Hi guys, can I get a shout out?
Hi, 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 hi.
Hey guys, can you hear me?
Yeah, we can hear you.
Yeah, we
Yeah, I
can.
can. Yeah, I can.
Why can't I? Sorry guys, I can't hear you. Hmm, let's see. Hey guys.
Hello? Yeah, we
Yep.
can hear you.
Thanks guys. No,
Hello.
sorry. I'm working on the borrowed computer, so it's all confusing. Um, Give me 1 second here, guys. Let's see. No, that was a bad idea. Shoot. I'm having a hard time today. Dial in. Okay, share screen. Okay, this is where we were, guys. So since I'm disorganized, I'm going to throw you guys off your stride by bringing up a stressful topic. So I'm thinking of having your first real quiz or quiz one next Tuesday. So a week from now, we're going to have our first quiz, and it's going to cover, PN junctions, and we'll talk a little bit about diodes. So basically, we're going to cover essentially chapter 2, the stuff we covered from chapter 2 of the book. And you have I think I already put the homeworks on. So my suggestions: do the homeworks, and so I'll put that also on the blackboard. Okay. So anyway, quiz one is next Tuesday. So that was the first thing. The second thing is kind of not really directly related to the class. I'm watching this YouTube channel from this prof, Stanford prof. He's a neuroscience prof, and I really like it. I really like this guy. I really like what he's covering, and he just started the podcast, and so he's only started since the beginning of the year. And the first month was all about what you can do to improve your focus, which has to do, with techniques with learning, with techniques to getting better sleep, um, being more alert, and I just really like it. So I wanted to tell you guys about it. It's called the Huberman. I think it's called the Huberman Lab. Whoops. Um, Huberman Lab. And so this is, along the same lines as the book I recommended. I think a lot of you, unless you have really good study habits, unless you got really good health habits, meaning that you're sleeping well, so you're staying alert, that kind of stuff, and unless you got a really nice environment to study, you guys are probably not doing, like, you're not getting the grades that you could get, or not learning, or not doing as well as you could. I'm pretty sure if you work on those things, like study habits, it's like a skill you have to learn. I never learned it, God knows, in undergrad, even in grad school. And I'm just looking at it now because I'm teaching and I can see it from the other side of the monitor here, looking at you guys. So it's just like a skill, like working out or whatever, which you got to build up. So, you know, study skills, staying focused, those kind of things are, I can guarantee you, at this level, unless you've achieved your peak, you're going to just bring up your GPA by 1 point at least, maybe 2, without doing a lot of work. So anyway, just my take it from me, from a guy who never did any of this in undergrad and suffered the consequences. Okay, anyway, so just really like this guy. Could be Huberman. Yeah, I think it's called the Huberman Lab. If that's not it, let me know, and I will send you an update. Thanks, Andrew Huberman. And he has a bulldog that snores in the background, which I like it even more. It makes me feel like I'm linked to the guy. Okay, so let's do a quick review of sort of basically everything we've covered so far, almost. Okay, so this is the main storyline. I would have liked you guys to have understood so far. So basically in a semiconductor, so this is in a semiconductor, we have the conduction or current. Conduction is caused by two things. So there's free electrons and holes. All right, free electrons are electrons that have sort of cooked off the atoms. There's some statistically, there's some number of electrons that fly off their bonds from the silicon atoms at a given temperature. Okay, so that's the free electrons, and holes are just an absence of those electrons in those atoms that they also move. So the free electrons are negatively charged. Their symbol is E minus. The holes are positively charged. Their symbol is H plus. Now, I don't know about the homework for sure, but I like for the test, etc. You guys don't need to know the equation for, and Ni is the number of free carriers, the concentration of free carriers in intrinsic silicon. So this was in your slides. And so if you don't do any, if you just have a pure 100% pure piece of silicon, the number of free carriers is 1.08 times 10 to the 10th per centimeter. These are the electrons per centimeter cubed at 300 degrees Kelvin. Okay, so this is a good thing to remember. And you just have to remember that as the temperature goes up, this can go up significantly and exponentially, etc. But this is kind of the number if I was going to remember one thing, it'd be that. And again, this is pure silicon. Okay, so then we talked about how we can adjust the carrier concentration by adding dopants to the silicon.
Wait.
Yes, go ahead. Did somebody have a question? No? Okay. So basically, so this is for a pure piece of silicon. So, which is, if you remember, silicon is from group 4 in the periodic table. Yeah. What's up, Arthur? Let me unmute you. Right? Let's see, how do I unmute you? Can you unmute yourself? Arthur? Arthur, did you have a question? Oh, he froze.
Lagging.
I think your voice is frozen.
My voice or Arthur's?
No, I think
think
he's trying to
Arthur's
tell
did.
you
Oh, I
that
see.
yours is
Yeah, it's Arthur.
frozen, but
Oh, I gotcha. Okay, got it.
No.
So Arthur was gonna tell me that my voice froze. Was his voice also froze? So there's something, or is it? Did I get that right?
yeah, that's what I assume at least.
Okay, I think Arthur's back.
Can you guys hear me?
Yeah.
Yeah, we can hear you.
Well, we didn't hear what you
All
said.
right. Thanks.
Okay.
Oh, you're frozen again, Arthur.
You need to unmute yourself, Arthur. Boy, this thing is hard. Can you?
I don't think you're frozen anymore, Arthur.
I think you're just muted. Yeah, it's a little bit of a challenge here. All right, guys, we'll let Arthur come back to us later on. To everyone, I'm going to turn off video for now. Okay, well, let's keep going, guys. Hopefully, we'll get this sorted out. If Arthur, if you have a question, just feel free to blurt it out later when you get when you're good to go. All right, so we can adjust the carrier concentration by adding dopants to silicon. What are these dopants? Well, so there we can add, so we can increase the number of electrons. By, let's see, by adding group 5 atoms to the silicon. So these would be phosphorus or arsenic. And because group 5 atoms have an extra electron in their valence band, every time you add a group 5 atom to a bunch of silicon, each one of those atoms gives off 1 electron into the semiconductor. So you're basically increasing the number of electrons. Okay. So, and we call these group 5 atoms, we call them donors. Okay. And their density so the density of donors, we put that as N sub D. And that's the units of that is, atoms per centimeter cubed. Okay. Similarly, we can increase, put this here, increase number of holes by add group 3 elements, atoms. And the most popular is boron. Okay, and these are called acceptors, and their density is specified as N sub A, density of acceptors 1 over, and the units is 1 over centimeter cubed. Okay, also a piece of silicon that has donors added to it is called N-type silicon. And one that has acceptors added to it is got P-type silicon. Okay, so let's see, what else do I want to say? Okay, so that was, so now we can get something to be having mostly electrons or mostly holes by design. We can actually build that in by adding these acceptors or donors. Okay, so now we're adding either electrons or holes that are things that cause the conduction in a semiconductor. So how do we get those things to move, or what mechanisms do they have to move? Where these electrons and holes have two mechanisms to move. Okay, so the first one is called drift. Okay, that's movement, and so this has an electric field associated with it. So this is movement of an electric field. If you put a positive or negative charge in an electric field, the electric field gets them to move one way or another. So, if the electric field, let's say, is pointed this direction, if you have electrons which are negatively charged, they'll move in the opposite direction to the electric field. Or, if you have holes that are positively charged, they'll move in the same direction as the electric field. Okay, so that is called drift. So that's one type of current, one method of conduction. And then, so we have, if you remember, we had a sort of a constant. It's not really a constant because it depends on the type of silicon, it depends on temperature, depends on a lot of stuff, but it depends. So we have the velocity of either electrons or holes is related to the electric field with this thing called mobility, which is mu sub n is so-called mobility of electrons. And this is not like a physical constant. This is like every chunk of silicon with some doping concentration, with some quality, with some temperature, has its own, mobility. And mu sub p is the mobility of holes. Okay, so that's these mu's, these mobility are the proportionality constant between the conduction, these conducting things in the electric field that's across them. Okay, the second mechanism was called diffusion. And this has got nothing to do with electric field. This is just purely has to do with stuff from a region of high density. Any like freely moving things likes to move from region of high density to region of low density. And these are anything, right? They don't have to even be electrically charged. The example was a glass of water with a drop of ink in it. The ink, if you look at it over time, it gradually spreads to the whole glass and it'll get evenly distributed over time. Okay, and so nothing to do with electric field. It just has to do with the density of these carriers. So density, or I should say density gradient of carriers. So to have this kind of current, you need to have regions of high density of electrons and holes and low density of electrons and holes. So, and then the electrons or holes will move from a region where there's a lot of them to a region where there's very few of them, and gradually you just get an even distribution if nothing interferes. Okay, and then the constant that that defines this is called the diffusion constant. So that's d sub n or d sub p. So this is diffusion constant. Oops. And again, every type, if you got a piece of silicon, you dope it a certain way, at a certain temperature, it'll have a certain diffusion constant. Okay. Everybody with me so far? You got any questions? Any questions? I'm just like, this is like high level stuff, so hopefully you guys are able to follow
Oh, I
this.
have a question.
Yeah, go ahead.
So I think on the right, in the box, what does that say? Is that mu p, and then
Yeah.
like something?
So, sorry, let me rewrite that. Okay.
I thought it was mobility.
Yeah, it is mobility. So it's mu sub n is the mobility of electrons. Mu sub p is the mobility of holes.
Wait, so the holes like move? No, not really, right?
No, they do move. They do move.
They do move?
Yeah, yeah.
Wait. I thought the electrons move, right?
Yeah. Okay. So let me show you guys something. Let me go back to, what was it? I had some drawings in. So I'm glad you're asking that question because it's a very, very important concept. Where were we? Okay, so the electrons, not every electron moves. It's only the electrons that have left a particular atom they're with. So for example, when there's high enough of a temperature, an electron can break off from the atom and start moving around the lattice. And notice this. So this is a statistical phenomenon. At some temperature, some electron gets enough energy to fly off into this rest of the silicon block. And it'll go around forever because, you know, if this is pure silicon, none of the other silicon, there's no place for it to land in. So none of the other silicon atoms can capture it. All their bonds are taken. There's nothing is positively charged, sort of floating around. Okay. Now, if that electron leaves, so for example, this guy, it leaves a hole or it leaves a lack of an electron. So for all events and purposes, if you just look at this particular atom, for example, it'll be positively charged because if it has all the electrons, it'll be neutral. If it's missing an electron, it'll have the charge of an electron, but the positive charge of an electron. Okay. Now this guy can actually move because, for example, it can switch places with this electron, with this bond. So this electron can jump here and this guy can jump here. They don't have to, like, that electron doesn't have to cook off. It just has to switch places with the hole and the gap moves to here. And then the gap can move to here, to here, to here. So it can move around the lattice without it's the lack of an electron that's moving in the lattice separately than the electron that cooked off and created that lack of charge. Does that make sense?
Wait, so basically an electron leaves and it switches with another one, and so are you saying the other one kind of goes to that first hole, or like?
So you gotta remember there are electrons. Just for a second, there's like what we call free carriers. Free carriers are just sort of floating around the material, around the semiconductor. So an electron can cook off and it'll be a free carrier, and you see it's moving around. It doesn't need to get captured, right? There's nothing to capture it. And it's very few of these. There's a lot of atoms, so they can move around for like a long time. Now the holes, which is that electron will leave a hole in that piece on that silicon atom, and that hole can move two adjacent atoms. Trying to think of what would be a good analogy for this thing, but
Wait, so it's not like moving, right? So it's just a different electron moves to that spot and then a new hole is created.
yeah, but these are not, it's not a new free electron. It just happens to be one of the electrons in the adjacent atoms to that hole.
Gotcha.
So it switches space and it's like the hole is moving.
I
If
see.
you like look at the effect of it moving across your semiconductor, it looks like a positively charged particle is moving around. Okay, and if there's an electric field, say here, pointing in that direction, this hole, this positively charged thing, you can imagine it's sort of has a preferred direction for movement in the direction of the electric field.
Gotcha.
Any other questions, guys? This is a pretty important topic, so we can stay on this until it really sinks in. I gotta admit, I never understood this in my microelectronics class, so hopefully some of you guys, most of you are getting that. So everybody's good?
Just one more clarification, I guess. So I guess just going back to that, so it's kind of like the holes moving around, moving through the electrons, kind of. So it's like the same hole, but it's like, how do I say? So it's basically it's the same hole. It's just moving around the electrons. Is it?
It's moving around the atoms. Yeah. So
The atoms. Okay.
Yeah. Moving around the atoms. So the way like a mass of solid silicon is just let's say it's pure silicon for the sake of discussion, and it's solid. There's just a bunch of atoms stacked next to each other in 3 dimensions, right? So every atom is got sort of like 4 neighbors, and like these holes are basically these lack of electrons can just move around, but they're sort of like getting handed off between neighboring atoms. They're like, just imagine if there's a place for an electron, a neighboring atom to go, if there's the temperature is high enough, it might decide to jump, in to this neighboring hole where there's a spot for it to jump to. And so by definition, there's a hole created where it was, and so on and so forth in the neighbors. It's like a statistical sort of phenomenon. So like at some point, high enough of a temperature, there's a hole, there's an empty spot next to you, you might just shift over to that empty spot. And then that way it looks like, if you just look at the empty spot, it actually looks like the empty spot is moving, okay, through something.
Okay, that makes more sense. Yeah.
Yeah, I'm sure there's an analogy in physical life, but I can't think of what it might be. So, okay, so that is a difficult thing, but also just remember, I just feel like I always need to say, because whenever I heard holes, positively charged particle, I was like thinking of positrons. I heard they might exist. Is it a positron? Is it something? If it hits an electron, is the world going to explode? No, it's just a lack of an electron. And the only reason this exists, again, is that because you are in a block of solid atoms, a solid block of atoms next to each other, and like that way a missing electron spot can get sort of handed off from one atom to another, because they're just all sitting adjacent to each other. So that's sort of the best. And it just looks like, this thing is moving in the direction is opposite to where the electrons are jumping in. Okay, so I'll see if I can find like a video or something that might explain it better. But that's all I got, Nelson. So Nelson, are you asking the questions? Nelson?
Yeah. Yeah. Thanks for that. That, I mean, it makes more sense now.
Okay. So just, again, there's a lot of stuff. There's a lot of background here for semiconductors. For the purposes of this class, you only need to remember that we have two types of free carriers in a semiconductor, electrons and holes. Holes have the same charge as an electron, but positive charge. So that's kind of think of it. So if you have an electric field, the holes move along in the same direction as the electric field. And if there's a lot of these missing points, a lot of these holes in one place and not so many of them in another place, they tend to distribute evenly. And then they have these proportionality constants of movement for mobility and diffusion. So that's like, you don't, there's a lot of physics explanations, semiconductor physics underneath this, and you're welcome to explore it, but you won't need to know all that stuff for this class. You just need to sort of pretend for a second that there's electrons and holes and they're moving in the semiconductor. Okay, so now there's a couple of other things I wanted to add another page here. A couple other things we need to remember. So I'm just trying to give you the highlights that most of the stuff you need to remember. There's a relationship called Einstein's equation. And it's kind of wild and it's kind of crazy because it relates these diffusion constant. This is the diffusion constant. This is this guy here that describes diffusion, and this is the mobility. So let's say this is d sub n, mobility. So these should be unrelated. One is a drift mechanism, one is a diffusion mechanism. They should be two unrelated constants. But it turns out that the ratio is equal to these physical constants. So K is Boltzmann's constant. You can look this up. Okay, this is like a thermodynamic thing. This is like honest to goodness constant in the universe. Doesn't matter what temperature you're at. Doesn't matter you're here on Mars, Alpha Centauri, the other side of the universe. It's a constant. Okay, temperature is temperature, right? It's sort of like something you can measure. It's a constant. I mean, it's not a constant, but it's a physical thing. It's like it is what it. So that's a temp. And Q is the charge of an electron, which is another physical constant. It doesn't matter where you are in the universe. The charge of an electron stays to be the charge of an electron. It never changes. So it's very strange. I do not have an explanation for you why this ratio is this ratio of these physical constants. But sort of as my old boss used to say, from the sublime to the ridiculous, for the purposes of our class here, of us 40 people, the important thing to remember out of this, because this ratio KT over Q will show up again and again. And the nice thing is that the thing to remember is that is about 25 millivolts at room temperature. Again, room temperature is defined as 300 degree Kelvin. I mean, so as you'll see, we'll use this shows up, this KT over Q keeps showing up in equations as like something you have to multiply by voltages and other stuff. And you basically have to kind of remember this 25 millivolts at room temperature. Most of the problems you'll have in this class, most of the homework tests, etc., I'm going to call out room temperature. So you can just use this 25 millivolts. This is magical thing that makes life easy. So remember that one. Okay, so that's one. The second thing you need to remember is, I don't know what this is called, but it's called the, that's the equation for relating Ni to to electrons and holes. Okay, so at forever and ever, for everything to do with anything, the number of electrons times holes is equal to the intrinsic carrier concentration squared. Okay, so what does this mean? Let's say you doped a piece of semiconductor, so you made it n-type, right? If I put donors in there and make it n-type, let's say I have that, then I can put such a huge number of donors in there that the number of free electrons there becomes approximately the donor concentration. Okay, so then I can just calculate the number of holes to be Ni squared over N sub D for this N-type silicon. And we call this, in this case, because this is so much, the number of electrons is so much higher than the number of holes in this case, this will be called majority carriers. This will be called minority carriers. Okay, or if I had a piece of silicon and I put in a bunch of acceptors there, I could make it a p-type silicon, and then the number of holes becomes the number of acceptors, and the number of electrons is Ni squared over number of acceptors squared. And these, in that piece of silicon, these are the majority carriers. And these are the minority carriers. Okay, so this is another important equation to remember. Okay. All right. Okay, so lastly, before spending all this, no, it's about 20 minutes. Okay, so now we said that you can take a piece of silicon that's pure, and you can dope one side of it. You can put a bunch of acceptors on one side of it, and that would make this side a p-type by our definitions. And you can put a bunch of donors on the other side, and it becomes n-type again with our definition. So that means this has a lot of electrons, and this has a lot of holes relatively. Okay, so this point is called the PN junction. Okay, that's the sort of the border between the P and an N. Okay, so you can just make that. You can take a piece of silicon, you can dope one side of it with a lot of acceptors, you can dope the other side with donors. You, as a semiconductor engineer or somebody who you're going to buy this thing from, made this thing. Okay, so this does something unusual when you do this, something unexpected. Now, now we don't have, when we build this, let's say it's just sitting there, right? We don't put any voltage, we don't put a battery here across this. There's no electric field initially. Okay, so these are just floating, P and N, just sitting on a table. So what happens? So there's a lot of holes here, not too many holes here. There's a lot of electrons here, not too many electrons here. So basically what happens is holes are gonna start going from here to here because of diffusion. Remember, diffusion things want to move from high density to low density areas. And then electrons want to go in this direction. Okay, because this has lots of electrons and this is lots of holes. Okay, so what happens then though is that because now these are two separate pieces of semiconductor, because you're losing electrons from one direction from here. Okay, so the electrons are moving to the other direction. So you end up having ionized atoms here that are just, these are not moving atoms anymore. These are just like the actual atoms. So let's say we got this to be N by adding phosphorus to this chunk of silicon. So these are actually atoms of phosphorus sitting there who have lost an electron. It's gone to the other side. And so now, because they've lost an electron, they become positively charged. Okay. Were you with me there? It's like it become ionized, but they're just sitting there, ionized atoms.
I have a question.
Sure.
Yeah. So the junction is the middle, right? But is the junction just like, what is the junction? Is it just like something splitting the two, or is it like just like that? And then you just put something in there, and then is it still there? The junction's still there, or?
Yeah. So let me tell you a little bit how about how this stuff is made, like World War III kind of thing. So what you do is you take a piece of silicon, and so this is just silicon. Then you have this expensive big piece of equipment. It's called an ion implanter. And what this guy does, you put your silicon in this piece of equipment called ion implanter. And so, like, let's say I want to make this part N. Okay, so that ion implanter, you give it a bunch of phosphorus, like you give it a gas that it breaks down and then creates phosphorus atoms, and then shoots them at really high energy. This thing has like really high electric fields. It just like it's bombing, like shooting cannonballs at this thing. So it's actually shooting phosphorus into this silicon. And you can make sure it only goes on this part by covering this part with something. I won't go into the how you cover it, etc. But we're just hammering this part with phosphorus atoms, and they have so much energy, they just slam into the silicon, they go deep in there, and then they stop somewhere, and that's where they sit. And so you're just sort of filling this piece of silicon, not filling, I mean, it's still relatively, but to the total number of silicon atoms, there's not a whole lot of phosphorus atoms, but maybe one out of every million atoms, one out of every million silicon atoms gets displaced by a phosphorus atom. Okay. Then once you've done that, you cover this part up, and then in this ion implanter, you then just hammer down a bunch of boron on this side. Okay, now this guy's covered. And so again, now this side of the silicon has a bunch of boron atoms. Again, 1 in a million becomes a boron atom that has displaced the silicon. And so where that mask is the boundary between those two. Everything on this side of the mask is bombarded with boron, everything, and becomes P. Everything on this side of the mask gets bombarded with phosphorus and becomes N, and this interface between them is the junction. It's just like the actual mask that they put in there to mask off one or the other basically defines that interface. So if that interface is very sharp, and I'm talking about from a distance kind of thing. It's like very abrupt. It's called an abrupt junction. So if I was gonna draw like distance x, it'll be right at some point, it'll go from N to P. I don't know why I drew it like that, but at like one actual very sharp point. Okay. It's so-called abrupt junction. When you make something like this, realistically, it's not like it's just perfect in line. You basically get something that's not really abrupt just because the masks aren't 100% good, and these bombarded atoms, they kind of like might go across a little bit here and there, but it's a pretty sharp transition between P and N. But it's all silicon. Both sides, it's like a piece of silicon, but here you have phosphorus atoms, and here you have boron atoms distributed in the silicon. Okay, does that help? You're not gluing two things together, or you're not pressing them next to each other. It's really one piece of silicon. You sort of put in phosphorus or arsenic in one side, boron in the other, and they just happen to be sitting next to each other. Does that help, Nelson?
Yeah, that makes a lot more sense.
Okay. Okay, any other questions? Okay, so let's get back to this what we had here. Okay, so again, you've got electrons leaving from this side and leaving positive ions here, and then holes are going, because of diffusion, holes are going to the other side and they're leaving negatively charged ions. Okay, so whenever you have positive charges that are just sitting there, they're not moving now. Remember, these are not moving charges. These are actual phosphorus atoms in the silicon material just sitting there. So these are and then you have negative, you basically have boron atoms that are sort of have an extra electron. So now every time you have this, you end up with an electric field from positive to negative, from these positive to negative charges. So as you diffuse, as this diffusion function works across the electric field, it by itself, even without a user or anybody applying an electric field, it starts building up its own electric field, okay, over time. As soon as as soon as this thing is created, there's just this diffusion starts happening, and then you get an electric field across this junction, okay? So you get an electric field build up, and make sure I'm being consistent here. I got P on one side and N to the other. So at some point, this electric field is strong enough that it stops the diffusion. So notice that this electric field, okay, is pointed in this direction. So let's just look at the holes for a second. So holes, because this is a P material, it's got a lot of holes here. So the holes ideally want to move to this side because of diffusion. But this electric field that got built up, because of diffusion, the electric field get built up, but the electric field is now pointing in the direction that's stopping the holes that want to move. It's pushing the holes that way. So at some point, it's exactly enough that it stops the diffusion of holes from here to here. And electrons want to move from here to here. And remember that the electrons, because they're negatively charged, the electric field that's pointed in this direction wants to push electrons back in that direction. And so at some point, the electric field is exactly enough to offset the diffusion of electrons to the other side. So that means you'll get into a sort of a static situation where you just end up with this electric field in across this abrupt junction, or any junction, across a junction. Okay. And again, this electric field is exactly enough to stop current, diffusion current from flowing. And then whenever you have an electric field, okay, so this is an equation that relates electric field to voltage or potential. So whenever you have an electric field, you also end up with a potential. So if you're rewriting this equation, ends up being E dx, and this is like, so this is x across your junction minus. So you end up with a potential, what's so-called potential barrier across a PN junction. Okay, why potential? Well, potential is because it's voltage, potential energy created by an electric field. Why barrier? Because it's acting as a barrier to the diffusion of free electrons across this junction. Okay, any questions, guys? Okay, so that was kind of a long-winded review, but what the heck? So now we're ready to pick up where we left. So I think I already talked about this, that the electric field is enough to sort of stop the movement, and we get this basically a built-in potential, okay? Or potential barrier, either you can call it either one. Now, there's one thing that confused me when I was taking microelectronics back in the day was how come, like, I always thought, like, you know, wait a minute, I'm not applying a voltage across this PN junction. What's going on? And so it's just this feedback effect coming from the diffusion of carriers and the fact that you have ions left over, blah, blah, blah. It's just creating a built-in potential across your PN junction, even when you do not have, you're not applying any voltage across this thing. Okay. So there's basically, you can figure out what value this electric field is, and therefore the voltage across this junction, by making the drift, sorry, this is the drift equal to the diffusion, etc. You figure out the, I'm not going to go into these integrals, etc. But this is the important thing to remember. This is the important equation. So this guy right here. Okay, so this says the built-in potential. So if you do not apply voltage across this junction, you just have yourself a PN junction. And let's say the P has a concentration, acceptor concentration of N sub A, and N has a donor concentration of N sub D. Okay, so this voltage across that junction is KT over Q. Remember, this is a bunch of physical constants, and at room temperature, this is approximately equal to 25 millivolts. Okay, so if you have a set temperature, that's like a constant relatively. Okay, times the natural log of the number of acceptors on the P side times the number of donors on the N side over this Ni squared, which is the intrinsic carrier concentration. So, and again, at room temperature, this is equal to 1.08 times 10 to the 10th electrons per centimeter cubed. Ni is, I'm sorry, Ni is, not Ni squared. Ni squared is then would be like 1 times 10 to the 20th. Okay. So this is the important thing to remember, is when you put your PN junction together by doping one side with this much acceptors and doping with the other side with this much donors, you end up with this voltage across your junction. Okay, so that's kind of what we need to remember out of this whole thing. Okay, so one more point I wanted to make here. One, notice that this voltage is a function of temperature because Ni is a function of temperature. I wrote it here at room temperature, but remember it's a strong function of temperature, Ni is. T here is also just temperature, so that will make it also a function of temperature. So this V sub 0 changes with temperature. Okay. The other thing to see here is we can basically adjust V sub 0 by how much we dope N and P side. And that's something, you know, some engineers doing somewhere to get you this device. So you can kind of tune that to tune V0. But the third thing to see is that that's like a natural log kind of dependency. It means that, you know, natural log, if you remember, does something like x natural log of x does kind of like something like that. Okay, meaning that it like flattens out at some point. So, you know, you just cannot change this very much because there's a natural log type function. Okay, everybody with me so far? So we can't change it very much. So there's a range of this, and as you'll see, it's a pretty limited range that you can have it across this potential. Okay, so this is this PN junction without anything applied to it. And now we have it, we have this PN junction as like a electric component, right? So let's see what we can do with it. So I'll, you know, again, the symbol for this thing, this is also called a diode. So PN junction is also called a diode. When you use it in a circuit, it's called a diode. When you're doing semiconductor physics, it's called PN junction, and the symbol is this. And so it's got a N side and a P side. Okay, so this is the same thing as this. I've just drawn it in the circuit symbol. Okay, so there's two ways you can hook this up. You can put in a voltage, make the N side higher than the P side. Okay, so plus minus voltage. So VR, which is the same as this drawing. Okay, I can make the N side a higher voltage than the P side. Okay, this is called reverse bias. Okay, so, well, what happens when you do that? Well, notice that when you hook it up like this, by adding more voltage here than here, you are increasing this potential barrier. So this way increases the potential barrier. Okay, so you're just sort of like making it more and more difficult for any current flow. So as you apply more and more voltage, sort of nothing happens. Like there's no voltage is gonna, as you put more and more voltage in this configuration, you're not causing any current to flow. Okay. So it's kind of like an open switch. Kind of looks like a switch that's open to some extent. Just no matter how much voltage you put on it, it kind of looks like an open switch. Now, one thing that it does do, and there's one application people might use it in, is as a voltage dependent capacitor, because as this junction width, as you're putting more voltage across this junction, you are increasing the size of the junction, and it's as if you've got two parallel plate capacitors and you're making the separation larger and larger. So in effect, if this is the capacitance of the junction and this is the reverse bias voltage, you can basically make the capacitance of the device less or higher by changing your voltage across it. So you can make a voltage dependent voltage controlled oscillator or something like that if you want to have a reference oscillator for, like a cell phone or something like that. Okay, so you just have to remember that you can change the capacitance across the junction, but for the rest, most of the rest of the class, okay, this is something people use in circuits, and you might see them in other parts of the book, in other classes that this book is used in, et cetera, but like, we're not going to really worry about this much in this class, but there's just one use for reverse bias, a reverse bias junction, which is a junction that's hooked up like this. For the most part, though, we're going to look at it, at least initially in chapter 3, as if it's just you're basically creating an open switch. You're opening a switch. That device is. Okay, so that's called reverse bias. Okay, interesting, but not that interesting. Okay, so now you can go the other way. You can take the same diode and you can hook up the battery in reverse. I call it some V sub F. So you basically are making the P side higher voltage than the N side, okay, which is the same as this drawing. This is just the way you draw it when you're analyzing a circuit. Okay, so now notice this is working in the opposite direction as the built-in potential. Okay, so the built-in potential was just enough to stop current from flowing, diffusion current from flowing. Now you're reducing that slightly by applying a voltage from the outside. So now, as you're applying this voltage, there's not quite enough current to stop the current flowing, so current starts flowing. And as you apply more and more voltage, more and more current starts flowing from basically across this diode. Okay, so basically you are starting a diffusion effect. So what you're doing is you are initially, basically there was enough that you stopped the diffusion, and then basically by putting in a voltage that takes away from so this equation is a rewrite of this equation here. Okay, we just move the natural log, sort of move the p's around, so we end up with this stuff being sort of exponential related. Okay, so the interesting thing is now when you have this forward bias in this way, you're basically increasing the amount of diffusion in an exponential way. Okay, so this is this forward voltage that you're adding, Okay, so the relationship is exponential, which is interesting. And then when you calculate it all out, I'm not going to go through the derivation. You end up with in forward bias. So now you're starting at a current. Okay, remember in reverse bias, you weren't really getting a current. In forward bias, now you're getting an exponential current. So that's what you end up with. Okay, and this I sub s is defined by this equation. So if I was going to do this and draw, so let me put up another page here. Actually, I'm just going to draw it a different one. I'm just going to flip the diode. So this guy's hooked up like this. Let's say I hooked up my diode like this. Okay, so then I draw this voltage V sub F in the horizontal axis, and I'm going to have the current through the diode be on the vertical axis. We'll get something like an exponentially increasing current. So this looks like sort of proportional to exponential of V sub F times a bunch of other stuff, but it's sort of an exponentially increasing current. Okay, so now remember, if I hook up my diode like this, I get very little current or no current. So I look like I have an open switch. Okay, if I connect up my diode this way, I have a lot of current. So after a while, it just looks like a closed switch, because you can get like a perfect switch has zero resistance. So if you put a voltage across it, you just get sort of an infinite amount of current. It's not quite infinite, but it's exponential. So it's a lot of current. Okay, so that's what it looks like in forward bias. I'm going to kind of, this stuff at this point isn't that important about charge gradients, etc. I'm going to just, you guys can look it up, but let me just jump into this. So this equation, okay, is the equation that like it's like the first equation you really have to remember. Okay, so this is the equation for a diode current, regardless of whether it's forward bias or negative bias. So if I put a battery across this diode, but I really drew that badly. And I have my bad days and worse days for drawing. So let's say I put a voltage here. This is my diode, okay? And let's say I take this voltage to be very positive. And, oh, actually, let me just to, sorry guys, let me just to make this the same as this graph, I actually have to draw it like this. Okay, so let's say I make this voltage very positive, very positive. Okay, I have this exponential, it's in forward bias, I have this exponential relationship. And let's say now this voltage becomes very negative. So now this diode is in reverse bias and I get very little current, almost no current. Okay. So basically this equation describes both sides of this graph. Okay. So for a second, I'm just, I sub s is this constant. well, we defined all earlier, but just for the second, let's forget about that. Call it a constant for a second. Constant. That might be, 1 times 10 to the minus 10 apps, let's say. Something pretty small, okay? But just think about this as a constant for a second and look at this part of the equation, okay? This V sub t is our old friend KT over Q. This is just instead of writing KT over Q, people call it V sub t, okay? And again, that's 25 millivolts at room temperature approximately. Okay, so if this diode was in room temperature, this would just be a constant 25 millivolts. Okay, so look at what happens to this equation as V sub D becomes very positive. In fact, as soon as V sub D gets a little bit more, or gets a little bit more positive than 25 millivolts, okay, as soon as it starts becoming more positive than 25 millivolts, this starts growing exponentially by definition, okay, and it quickly becomes much, much larger than 1, okay. So when you're applying a positive voltage V sub D over here, you can basically assume that this 1 is, is much smaller than this. So you can just assume shorthand that this is approximately the case, just this part. Okay, out here, this is where you assume that the 1 is very small, and you can just use that. Okay, now let's look out here. Okay, as V sub D becomes very negative, this ends up being 0. Okay, you have exponential of a negative number, or a big negative number ends up being equal to 0, and you just end up with this minus 1 times I sub s. Okay, so you just end up with minus I sub s current flowing across. Okay, so, and then I sub s is a function of, we defined it here, it's a function of, this is a constant, this is, 1 times 10 to the 10th squared at room temperature. We define that. This A is the area of the junction. And these are sort of how much you dope the junction by. And these define this I sub s. Sometimes you have to calculate it, sort of in chapter 2. Some of the homework problems might ask you to calculate it, maybe something on the quiz to calculate it. But for the rest of the class from chapter 3 on, you'll be given this number, because in reality, or in the lab, etc., you'll be buying a diode, or you'll be given a diode, and that's already like has this sort of defined by the way they created that diode. Okay, so I'm going to leave it here, guys. We're kind of out of time, so I'll leave it here. So this is a very, very important equation to remember, okay? And this behavior, exponential on when it's forward biased, and basically sort of off when it's reverse biased. Any questions? Okay, if not, I'll let you go, guys. I'll put remember the quizzes next Tuesday, and hopefully we'll cover everything on Thursday, etc. I think we will. So I'll put that on the Blackboard, the notice about the quiz. All right, guys, take care.
Thank you.
Thank you, Professor.
Thank you.
Thank you. Bye.